back. So in the last video we saw a simple problem, simple example of multi-stage decision making problem where an agent has to travel from one cell number 1 to cell number 36. There are some obstacles are there. In each cell the agent can take 4 actions, left, right, up and down. There are some obstacles are there. It has to reach the goal state in minimum number of steps. That was the problem. So this problem could be solved using reinforcement learning. And how do we design an algorithm for this? We have to decide what is state. Then we have to decide what is state space, action space, reward, state transition function, and a reinforcement function. Reinforcement function is the most appropriate name. Sometimes people may say reward very loosely. So what is state for this problem? The state of the system should capture the information required to make the decision. So in this simple example, the state is your designer, in this case myself, are deciding what is the state. It's the part of the solution, okay? The choice of state is part of the solution. So I decided that the state is just one number. The cell in which the agent is currently present. It needn't be one number, it could be a set of numbers. If you are actually talking about a real robot, it will have its positional coordinates, x coordinate and y coordinate, plus its orientation, plus this proximity sensor values. It could have many things. What is state space is the possible values the state can take. In this example, the possible values the state can take is 1, 2, etc. up to 36. What is action space? 1, 2, 3 and 4. What is an action? An action could be one of this. What is state transition function? So when you write the code, you may have to take care of some special cases. In general, state transition is, I have modeled the problem such that 1 stands for right, action 1 stands for right, action 2 stands for left, action 3 stands for up, action 4 stands for down. Let us consider a general state here, 10. If I am in 10 and the action is 1, I will move to 11. If I am in 10 and the action is left, I will move to 9. If I am in 10, action is 3, I will move to 4. If I am in 10, if action is 4, I will move to 16. If transition results in crossing boundaries, the agent will remain in the same cell. So if I am in 6 and I take an action right, I will remain in 6 itself. So you should modify these equations to capture that. If I am in 1 and action is up, I cannot go up. So I will remain in 1 itself. So this is the state transition one. This is a very simple example. So depending upon the situation, you should capture the state transition function. So if you are actually using reinforcement learning, using an actual robo, so robo will have all the sensors. When you take an action, it will reach another position and the proximity sensor value, the orientation value, everything will change. So it will come automatically. But if you are simulating, you should take care of all these things. So RL can learn. RL does not require a mathematical model, but it has to interact with an environment or a simulation model. So another major design tool for reinforcement learning is reinforcement function. And denote it as Rk is equal to G of xk, ak, xk plus 1. So in this particular problem, 15, 17, 18, 20, 26 and 32 are block states. So this is a design thing, okay. I can design the reinforcement function. This is part of the design. So I don't want to hit the block. So I am in 9. If I go down, I'll reach in 15. So when I reach in 15, it's a blocked state. So the robo cannot move further. And the reinforcement is 100 or the cost is 100. Whereas if I am in 9, if I take a right action, the cost is 1 because it's a normal state. So reinforcement function, when you design, when you read papers of complicated papers, complicated systems, you should consider, you should look how they have designed the reinforcement function. Then another term which you should know is policy. I have put in my prelude, policy is a mapping from state to action. Let me repeat again. In my first video, I told about single stage decision making problem. There is no concept of state there. You have to make one decision. And that decision has to be the best decision. Here, you are taking a sequence of decisions. So, for this, you require a policy. What is a policy? It's a mapping from state to action. Or policy or strategy is the rule by which the agent selects an action in state X. You are in X. If you give it to, say, a function, it should give me the action. Pi of x could be A. Another important concept in Q learning is the Q values. It was the contribution from Dayan, and in his PhD thesis, so you could look into that if you want to. So this idea about Q values revolutionized, was a quantum jump as far as reinforcement learning was concerned. QXA tells you how good it is to take action A in state X. So QXA, to be precise, it's called optimal Q values. So if you know Q, I'll repeatedly tell about Q values in this video so that the concept is clear. It tells you how good it is to take action A in state X. Say you are in state X and there are 4 actions. If Qx A1 is 90, Qx A2 is 7, Qx A3 is 10, Qx A4 is 100, then Qx A2 is the best one. It tells how good it is to take action A in state X. I'll make it a little more clearer. So this is the policy. Policy is usually in reinforcement learning literature is denoted by pi. Pi, it could be a lookup table, it could be a neural network, it could be a function. You plug in X, you will get A. For our problem, there are possible number of policies is 4 raised to 35. So to understand about Q star XA, let us understand Q pi XA. What is Q pi XA? Q pi XA is the expected long-term reinforcement when the agents start in state X, take action A in the starting state, and thereafter follow an optimal policy. Suppose one policy is always move right. Suppose a policy is always move right. So let us consider you are in state 1. Always move right, and so let us find Qx left. Qx left means, suppose x is say 8. Suppose x is 8. What does Qx left means? At 8 you will take a left action. After that you will follow the not the optimal, the policy pi, that is always move right. So the total cost incurred in this case will be infinity. Okay. So the first action is move left. then you move right, then you move right, then you move right, then you are here, move right, you reach 12, and then you keep on moving right. So that will result in the total cost for that in for one simulation is q pi xa is infinity. Okay, so what is qxa? It is the long term expected cost if you are in state x, take action A, thereafter follow the policy pi. More interesting is the optimal q value or qxa without any argument. Q star xa is the long term, is the expected long term reinforcement when the agents start in state x, take action A in the starting state, and thereafter follow an optimal policy. Qxa is given as expected value of sigma, expected value of sigma k is equal to 0 to n minus 1 gamma raised to k g xk ak xk plus 1, where x0 is equal to x, a0 equal to a, and ak is equal to pi star xk. What does it mean? It means you are in some state, initial state x, you take action A irrespective of the optimal policy, and thereafter follow optimal policy. So let me bring that figure here. Let me copy this table here. So here, what is there is an optimal policy there. So the optimal policy is if you are in 10, you have to go down. If you are in 34, you have to go right. If you are in 4, you have to go down. So the optimal policy, let me mark it. The optimal policy, suppose God has given you the optimal policy. Here it is down. Here it is down. Here it is down. Here it is right. So in every cell, suppose you know the optimal policy. Now what is Qx? What is Qxa? So let us consider Q2L. Let us consider, where's my pen? Yes. Suppose let me consider Q2 left. If I consider Q2 left according to this definition, what is it? You are in 2, you take left action. When you take left action, you will move to cell number 1. When you move to cell number 1, thereafter you will follow the optimal policy. From cell number 1, what is the optimal policy? Go right. So let us count it. You are in 2. You are in 2, you took one left action. After that you follow optimal policy. So it's 1, then move right 2, then move right 3, then move right 4, move down 5, move down 6, move down 7, move down 8, move down 9, move right 10. So Q2L will be 10. Q2L will be Q2L will be equal to 10. Similarly, you compute Q2 up. Q2 up will be first you will take an up action, thereafter you follow the optimal policy. Q2 up also will be what? Q2 up also will be 10. Q2 down, you take down action. you take down action 8, then thereafter you follow optimal policy. What is the optimal policy here? 1, 2, 3, 4, 5, 6, 7 and 8. Q2 down is 8. Q2 right also will be 8. So Q2 left is 10, Q2 up is 10, Q2 right is 8 and Q2 down is 8. So it shows that going right and going down are good. So if you know Q star XA, suppose you don't know optimal policy, but you know Q star XA, that is the catch here. If you know Q star XA, then you know the optimal policy. So suppose Q x prime A star is less than or equal to Q x prime A for all A, then A star is the optimal action. So if you know Q star without knowing the optimal policy, you can get A star. So in this example, going right as well as going down is equally good. So when there is a conflict, when you are finding minimum, you should resolve the conflict. You could toss a coin. Toss a coin means you could generate a random number between 0 and 1. If it is less than 0.5, take A star to be right, or if it is greater than 0.5, you can take A star to be down. So there could be solutions, there could be multiple optimal actions. If you are, it happens, isn't it? If you are along a rectangle, if you are driving and there's a rectangle, the road is a rectangular section. It's not you want to go here in this direction. You are here now. You could either go in this direction and then go right, or first you can take right and then go forward. So both are fine. So reinforcement learning can handle problems with multiple optimal solutions. Okay, it will take one of them, or it could take. You can have a stochastic optimal policy. So it won't be giving you. This is slightly on a higher end. It won't be giving you an optimal action. It will give you a probability distribution. So where you are in state X, you will take your optimal policy will be a probability distribution. If you don't understand this, don't worry. Say for example, you are in state 2. So instead of saying go down, pi star of 2 will be a probability distribution. So where going right will have a probability of 0.5 and going down will have a probability of 0.5 and going left and going up will have probability 0. Whereas when you are in 16, going down will have probability 1 and going left, up and right will have probability 0. So reinforcement can learn optimal stochastic policy also. But don't worry, we will consider deterministic problem to understand the terminology. So what I want you to be very clear is, I want all of you to be very clear about the meaning of Q star XA, the optimal Q value. And if you know optimal Q value, you know the optimal policy using this equation. So you remember in our Enna-Bandit problem, I told you about the Robin-Monroe algorithm, where if you are trying to evaluate an expected value of something, a random variable, a random quantity, you can do it using this iterative formula. What is Q nu? Q nu is Q old plus alpha into error. What is alpha into error? I have put as my footnote for all slides because such an important equation. Your observation XA minus current estimate. You want to estimate something. So you are getting some observation and you have an old estimate. So error is current observation minus old estimate. So this is so you ponder about this equation further, you read further, you look into Sutton-Barto book. So to start with, you start coding with this equation. This is my current estimate, current observation. Based on current observation, I think this should be the Q value, because Q value is defined as the, I'll give an intuition for this expression. Q value is defined as the total expected cost. If you start from state X, take action A, thereafter follow policy pi star. So if you are in state xk, you took action ak, then one step cost is q xk ak xk plus 1. And what is the cost from xk plus 1 to the terminal state? That is, according to the definition, what is q xk plus 1 a prime? Q xk plus 1 a prime is the cost, the total expected cost. If you are in state xk plus 1, take action a prime and then follow optimal policy. So qxk plus 1 a prime, in our case, will have 4 values. We know that after the first action, we are following optimal policy. So in the second step, you take the optimal action. So that is why that min is there. So think about it. Maybe you can ask me when we meet. So once you understand this, then this equation is clear. So by what people have proved that this, if you keep on updating this, and if alpha satisfies some technical condition, that is sigma alpha is equal to infinity and sigma alpha square is less than infinity, that the sequence converges, then if you start with any reasonably good Q value, say take all of them zeros or take all of them between -1 and 0.1 random numbers, then the Q values will converge to optimal Q values. Once you get the optimal Q value, then you are done. Once you get the optimal Q value, you are done. You will get the optimal policy as using that argmin formula. Once you get the optimal Q value, suppose these are optimal Q values, you know the optimal action by taking argmin. So I'll take a small break here and then get back. Thank you.